In this video, I'll show you everything you need to know about ExpressLRS and its configuration. We will go over the available hardware variants and walk through binding and setting up both the transmitter and the receiver. Before we move on to the main topic, let's start with a quick introduction to what an RC link is and what options are available. RC link is of course the radio connection between the transmitter and the receiver through which you control your vehicle. It determines your range, latency, and connection stability. There are many different RC systems on the market. On one hand, we have classic solutions from companies like Futaba, Spectrum, or FrSky, which have been well known in the RC hobby for years. These are closed systems, usually very stable and easy to use, but at the same time not very flexible. On the other hand, we have long-range systems such as Crossfire or ExpressLRS. These systems offer significantly greater range, better signal penetration, and far more configuration options. Traditional systems work well over shorter distances and are often the default in ready-to-fly RC models, but if you want to fly farther, long-range systems are the way to go. The second factor is latency. The lower it is, the more direct the control feels. This is especially important when flying drones, freestyle or racing quadcopters. And the third factor is flexibility and configuration options. Closed systems are simple but limited. You are restricted to the hardware produced by a given company and the features they provide. Open source systems like ExpressLRS give you far more possibilities, with a wide range of configuration to suit your different needs. In the FPV world today, ExpressLRS is one of the most popular control systems. Like any RC system, it consists of a transmitter and a receiver. A transmitter module can be built directly into the transmitter, or it can work as an external module that you plug into your transmitter. On the drone, you simply have a receiver that picks up the signal, just like in any other RC link. Let's start with the basics. One of the most important aspects of ExpressLRS is frequency band it operates on. ExpressLRS can work in two main frequency ranges, 2.4 GHz and 900 MHz. You can also find dual-band transmitter and receivers. You might come across different module names or hardware from various manufacturers, but the key thing is which band they belong to. When it comes to physical differences in hardware, 2.4 GHz uses smaller antennas, while 900 MHz uses larger ones. A lower frequency means a longer wavelength, which is directly related to antenna length. Most commonly, antennas are a fraction of the wavelength. In our devices, quarter-wave antennas are the most popular. The 900 MHz band offers greater range and better obstacle penetration. However, performance on 2.4 GHz is already so good and reliable that in most cases you won't reach its limits. Many pilots easily achieve ranges of tens of kilometers. But that's not all. The 2.4 GHz band is much wider and has more available channels worldwide, which makes it better suited for situations when many pilots are flying at the same time. In such situation, the 900 MHz band can become overloaded, leading to reduced signal quality. Dual band modules are very useful in this case, as they let you adjust the frequency depending on your needs. As I mentioned, there are different setup options. Some transmitters come with built-in ExpressLRS modules, and you can also have external modules plugged into the radio. I recommend the setup when you have a transmitter like the Radiomaster TX16S or a similar one, with a built-in 4-in-1 module plus a separate external ExpressLRS module. The 4-in-1 2.4 GHz module contains multiply RF chips that together supports a wide range of RC protocols, including FrSky, FlySky, Spectrum, and many others, over 70 protocols in total. This covers the vast majority of receivers used in drones, RC airplanes, and even RC toys. On top of that, you add an external ExpressLRS module, which becomes your default control link. This makes your transmitter a very versatile device that can control a wide variety of vehicles. However, if you only need ExpressLRS and want the most budget-friendly option, a transmitter with a built-in ExpressLRS module will be perfectly sufficient. Let's move on to receivers. The receiver in your drone must of course operate on the same frequency band as the transmitter. So there are 2.4 GHz receivers, 900 MHz and also dual band ones. In the case of dual band receivers, you can switch the frequency in the software settings. They simply change which band they operate on. Their antennas are specially designed to support both frequencies, combining two antenna lengths. The downside is that they are not perfectly tuned for either frequency, so their performance will be slightly lower compared to receiver designs specifically for a single band. That said, they are still very good receivers, and in practice you probably won't notice the difference. As mentioned earlier, ExpressLRS is an open source project, and its GitHub repository is where you find the source code developed and periodically updated by its contributors. However, the hardware itself is not manufactured by the ExpressLRS developers. Any company can produce compatible devices and adapt them to this firmware. That hardware is still tested before receiving official support from the ExpressLRS developers. This approach is very beneficial. Hardware availability is wide, and everything is cross-compatible as long as you stay within the same frequency band. You can mix transmitter and receiver from different manufacturers. The system continues to evolve. Manufacturers compete with each other, which improves the quality over time, and prices remain attractive. However, it's important to pay attention to the quality of the hardware you're buying and choose proven manufacturers, because lower quality products can still appear on the market. On the ExpressLRS website, you will also find a lot of information and a complete knowledge base. It's definitely worth going through because it contains pretty much everything you need to know. Before we move on to software configuration, let's take a look at the hardware. Modules come in two main form factors, JR and JR Nano. The standard JR format is typically used in larger radios like the Radiomaster TX16S, including older transmitters, while the Nano format is newer and commonly found in smaller radios such as the Radiomaster Zorro. Nano modules can also be used with full-size JRI base via adapters. The simplest approach is to just buy a module that matches your transmitter. In our case, that would be the Radiomaster TX16S along with the Beta FPV Micro TX module in the full-size JR format. It's also worth noting that these modules are usually powered directly by the transmitter, so it's essentially plug and play. However, in some cases, especially when using higher output power like 1 watt or more, external power may be required, most often via an additional battery with an XT30 connector. That said, such high power levels aren't commonly used. They are mainly reserved for achieving exceptionally long-range flights. So, we plug in the module and screw on the antenna. Always remember to power on your transmitter with the antenna properly attached. Otherwise, the module may output power without an antenna connected, which can damage it. As for receivers, they also come in different variants and form factors. In drones, we typically use a flight controller, and wiring is quite straightforward. The receiver connects to the FC using the Crossfire protocol via standard UART port. A typical receiver has 4 pins, 5V, ground, TX and RX. You connect these to the UART pins on the FC. This setup is standard for any vehicle with the flight controller, while all devices are connected to and managed by the FC. Depending on the flight controller, connectors may vary. Sometimes you can use a plug, but in many cases, especially with copter FCs, you will need to solder wires directly to pads. In our case, we have a dedicated connector that plugs into specific pins on the FC mapped to a default UART intended for the RC link. Our receiver has already wire soldered to the correct paths, so we just need to connect it to the appropriate UART on the FC. You can also find receivers with PWM outputs. These have their own pins, often come in larger casings and look similar to classic RC airplane receivers. They are a great solution if you are building a plane that you plan to fly in manual mode without the flight controller. In that case, you need direct outputs from the receiver to your servos and ESCs. Most of these receivers actually support both options at the same time. In addition to PWM outputs, they also provide a serial crossfire output, so you can still connect them to a flight controller if needed. Before we move on to configuring our equipment, I would like to show you something we've been using in our work and also while recording this video, which is a desk from FlexiSpot that we recently received from them. It's the E7 Pro model with a large 80 by 200 cm chipboard tabletop. The surface is big enough that we currently use this as both a workbench and a table for recordings and equipment presentations like this one. What really stands out about this desk is electric height adjustments with a load capacity of up to 180 kilograms. You can easily adapt it to your office or workshop setup and adjust it to your preferred working position. There are many available configurations, including different tabletop sizes, materials, colors, and leg finishes. We went with the largest tabletop options specifically for working on our aircraft projects. You will find a link to this desk in the description. Alright, let's get back to configuration, starting with a look at the Lua Script, which is a small app configuration menu on your transmitter. At this point, it's worth mentioning that most modern radios run either OpenTX or its successor HTX. The operation, settings and menu layout are practically the same. Transmitters themselves are a broad topic. There's a huge selection on the market, but most of them offer the same core functionality as shown here using the Radiomaster TX16S as an example. After pressing the Sys button, go to the Tools tab and look for ExpressLRS. These are the settings we'll be working with later in this video. Many of the basic configurations are also accessible directly on the module using a joystick, so you can operate it even without the Lua script. Modern transmitters, especially those with built-in ExpressLRS modules, usually come with this script pre-installed. However, if yours doesn't, we will show you how to install it. Go to the ExpressLRS web flasher in your browser and click Download ELRS Lua Script. Then connect your transmitter to your computer via USB and select the USB storage option. From the available folders, open Scripts, then Tools, and paste the downloaded file, elrsv3.lua. As you can see, it's already installed here. Once that's done, we can move on to updating the firmware. There are several ways to do this, and it's not always required for proper operation. However, it's safer to make sure that both your receiver and transmitter are running the same firmware version, and it's good to update to the latest version from time to time, as it may include some improvements and bug fixes. I will show you how to update firmware using Wi-Fi, which is a quick and simple method, and we'll start with the receiver. To download the correct firmware, you can use the ExpressLRS configurator, available from the ELRS website or directly in your browser. Let's start with the desktop app. First, select the version you're interested in, preferably the latest one. Then choose the target. In our case, the manufacturer is Matex Systems, and the receiver model is R24D 2.4 GHz. Next, we have regulatory domains. You can choose the standard global ISM band, industrial, scientific and medical, sometimes also referred to as FCC, which stands for the Federal Communications Commission. There's also LBT, Listen Before Talk, which is adapted to European regulations. Briefly explaining the difference, in ISM or FCC, the transmitter sends data without checking if the channel is free. This provides better responsiveness and longer range, but it may cause interference with other devices. In LBT, Listen Before Talk, the transmitter first checks if the channel is free before transmitting. This increases latency slightly and can reduce performance and range, but it minimizes interference with other devices. This firmware also limits maximum transmit power to only 100 mW. So while LBT has some limitations, it should be used in Europe to stay compliant with radio regulations. In short, use LBT in Europe and ISM or FCC elsewhere. Next, we have the binding phrase option, which allows quick, automatic binding, but we will cover that later in this video, so for now leave it unchecked. After clicking Build, the firmware will be prepared and downloaded. You can also do the same thing without installing any app by using the ExpressLRS web flasher. The interface looks very similar. Select the same options, choose your hardware, leave the rest as default, and continue to download. The result is the same firmware file saved to your computer. Now we need to upload the firmware to your receiver, and for that it has to enter Wi-Fi mode. By default, you just power it on and wait about 60 seconds. After that, the LED on the receiver will start blinking rapidly, which means it has entered Wi-Fi mode and is broadcasting a Wi-Fi signal you can connect to. On your computer, connect to the ExpressLRS RX network. You will then be automatically redirected to 10.0.0.1, which is the default IP address of the receiver's Wi-Fi interface. From there, you can view and edit some settings, as well as update the firmware. Upload the file you downloaded earlier and start the update. The process is quick, and when it's done, the receiver is ready to use and bind with the transmitter. Before we do that, let's also update the firmware on the transmitter module. Go back to the ExpressLRS configurator and build firmware for your module. In our case, it's the Beta FPV Micro TX module, 2.4 GHz, 1 W. Choose Wi-Fi as the flashing method, leave the binding phrase unchecked for now, and proceed. Now go to your transmitter and in ExpressLRS Lua Script enable Wi-Fi mode. Just like with the receiver, connect to the ExpressLRS TX network. You will be redirected to the same configuration page. Upload the firmware file and your transmitter module is ready to go. Now it's time for binding, which means pairing the receiver with the transmitter module. First, you need to put the receiver into binding mode. There are several ways to do this depending on the model. Some receivers have dedicated bind buttons. However, the default method is the one called power cycle, meaning you power the receiver on 3 times quickly. Plug and unplug power 3 times in short intervals, under 2 seconds. After that, the LED on the receiver will start blinking in short double pulses. This indicates binding mode. Now you need to initiate binding on the transmitter, for example via ExpressLRS Lua Script options. Keep in mind that you need to do this within 60 seconds, otherwise the receiver will exit binding mode and switch to Wi-Fi mode. This timeout can be changed in the receiver's configuration page, but the default 60 seconds is usually optimal. Binding only takes a few seconds. Once it's done, the LED on the receiver will turn solid, indicating that it's successfully paired, and the radio will start receiving telemetry. This method is the default way of binding ExpressLRS, and while it might seem a bit unusual at first, it's actually very convenient. If your receiver is mounted deep inside your vehicle, you don't need to physically access it during updates, you just trigger the power cycle sequence. Now let's move on to another very useful method, which we use for all our aircraft, binding phrase. To do this, you need to build firmware again for both the receiver and transmitter. Leave all settings the same, but this time enter a binding phrase. This time we will enable Wi-Fi mode on the transmitter using the joystick directly on the module, just to demonstrate it. The process is the same. Connect to the ExpressLRS TX network and upload the new firmware through the configuration page. You might notice that the interface looks a bit different now. That's because the module is running a newer firmware version with some visual changes. Repeat the same process for the receiver, entering exact same binding phrase. Put the receiver into Wi-Fi mode again, connect its network and upload the new firmware via the configuration page. Now all you need to do is turn on the transmitter and then power the receiver. Binding will happen automatically. You don't need to do anything else. This method is extremely convenient, especially if you use one transmitter with multiple models. When building a new aircraft with a new receiver, you just set the same binding phrase, and that's it. No additional steps required. Let's also take a look at telemetry, which is the feedback data sent from the receiver back to your transmitter. You can access this in the model settings under the Telemetry tab. Sensors are detected automatically and can provide all sorts of data. Signal strength, flight mode, GPS position if available, as well as data from accelerometers, barometers, gyros, and more, depending on what sensor your flight controller has and what additional hardware is connected to it. Now when the hardware is ready, let's go back to the ELRS script and go over some of the basic settings. The first one is packet rate. In simple terms, this defines how many data packets per second the transmitter sends to the receiver. The higher the rate, the lower the latency. On the other hand, lower packet rates provide longer range but increase latency, so the right setting depends on your needs. If you're flying racing quads, you want the high packet rate and very low latency. If you're flying long range, a bit more latency doesn't matter, so you can choose a lower packet rate and gain more range. As a default, 250 Hz is a good middle ground. Here I'm using 500 Hz, which is also solid all-around choice. Let's go a bit deeper into this so everything is clear. As you can see, there are different packet rate options, which can be grouped into few categories. First, basic packet rates. 50, 150, 250 and 500 Hz are standard modes that use LoRa modulation, offering very good range and strong resistance to interference. LoRa, short for long range, is one of the radio modulation methods used in ExpressLRS. It transmits long, spread out signals that can travel very far, even at low signal strength. It also has very high sensitivity, meaning it can receive extremely weak signals. Receiver sensitivity is the minimum signal power it can detect, is shown in the brackets. For example, -105 dBm at 500 Hz. Sensitivity increases as packet rate decreases, reaching around -115 dBm at 50 Hz. The higher the sensitivity, the weaker signals the receiver can pick up, and that translates directly into greater range. We also have F1000 and F500 modes, which use a different type of modulation called FLRC. These are essentially the opposite of LoRa. They transmit short, fast signals, resulting in very low latency, combined with high packet rates, 500 Hz or 1000 Hz. These modes are mainly intended for drone racing, where even a few milliseconds make a difference. However, this comes at the cost of reduced range and weaker signal penetration. Then there are D500 and D250 modes, where the same data packets are sent multiple times to reduce the risk of packet loss. In D500, the base rate is 500 Hz and each packet is sent twice. In D250, the base rate is 250 Hz and each packet is sent 4 times. This improves link quality but slightly increases latency and reduces range. These modes are great for freestyle flying or situations where multiple pilots are flying together and interference may be an issue. Finally, we have 333 Hz full and 100 Hz full modes. These provide full 10-bit resolution across all 16 channels. In other modes, you typically get 8 to 12 channels, where channels 1 to 4 have full resolutions, and the remaining channels operate in a simplified way, often as 2-position or 6-position switch channels. The full mode is especially useful in fixed-wing models when you often use many channels at the same time. For example, to control surfaces, flaps, landing gear, a gimbal, and other components. In such cases, having the full number of channels and full resolution really matters. When it comes to channel mapping, channel 1 to channel 4 are the primary channels responsible for sticks, roll, pitch, throttle, and yaw. These always operate at full 10-bit resolution and behave the same regardless of their selected mode. The remaining channels are aux channels, typically assigned to switches and knobs. By default, they don't have full resolution and work as mentioned, as 2-position or 6-position channels. Only in full mode, all channels get full resolution, allowing smooth control to components that require precise movement. In practice, especially in FPV, you will usually stay within the basic number of channels, so choosing a standard mode is more than sufficient for most applications. Now let's talk about telemetry radio. As we showed earlier, the transmitter receives telemetry from the receiver, and this is enabled by default. Here you can define how often the receiver sends data back to the radio. For example, 1 to 8 means telemetry is sent every 8 control packets. 1 to 32 means every 32 packets, and so on. You can choose different options, including disabling telemetry completely, but the simplest and the best choice in most cases is standard. In our current setup, we have a packet rate of 500 Hz, meaning the transmitter sends 500 control packets per second to the receiver, and a telemetry ratio of 1 to 128, meaning telemetry is sent every 128 packets. So 500 divided by 128 is about 4, which means telemetry is updated about 4 times per second. This standard setting works well, because the system automatically adjusts it to match the packet rate, ensuring that telemetry is sufficient without interfering with control performance, since higher telemetry ratio can slightly increase latency. Sometimes during flight you may see a telemetry loss warning, even though your RC link is still solid. If you are losing telemetry frequently and at short range, you can try increasing the telemetry ratio, for example changing from 1 to 128 to 1 to 64. Disabling telemetry only makes sense in extreme scenarios, such as drone racing, when you are flying at short distances and don't really need telemetry during the flight. In that case, turning it off can slightly reduce latency. For most other use cases, it's not worth disabling. Now let's look at switch mode, where you can choose between wide and hybrid. This setting determines how aux channels, channel 5 to channel 12, meaning switches and knobs behave. As mentioned earlier, channels 1 to 4 are your main stick inputs and always have full 10-bit resolution. The remaining aux channels are affected by the switch mode. First, aux1, which is channel 5, is typically used as the arming switch and is always 2-position, except in full modes where all channels have full resolution. In hybrid mode, aux channels operate in 2, 6 or 16-position modes depending on the channel, which reduces latency. In wide mode, switches can use up to 64 positions, giving much smoother control at the cost of slightly higher latency. By default, it's best to leave this on wide, so you have that extra flexibility available. Next, we have link mode with 2 options, normal and MAVLink. Normal mode is the standard option and works in all cases, simply providing regular telemetry from the receiver. MAVLink mode enables full communication over a single radio link, including connection to a ground station, for example mission planner. In practice, this allows you to replace a separate telemetry radio. Everything works over one link. The transmitter receives full telemetry from the flight controller, for example running autopilot, and then can forward it to a ground station, typically via USB or even Wi-Fi using an option called backpack. This way, you get full access to live data on your ground station. You can monitor parameters in real time, plan missions, and modify them during flight. In this mode, the telemetry ratio is forced to 1:2, meaning very frequent telemetry updates, and switch mode is also forced to hybrid. This is because Mavlink requires a large amount of data and continuous stable communication, so some options need to be limited to prioritize telemetry. It's also important to understand that in this mode, control and Mavlink telemetry share equal priority, which increases the overall load on the link and results in higher latency. In normal mode, control always has the highest priority. Another key point is that this works well mainly on 2.0 GHz. On 900 MHz, data transfer is significantly slower, and the difference can be large enough that this setup may become impractical. This is a great option for fixed-wing aircraft and automatic flights, planned missions, long-range flights, and similar use cases. For typical FPV flying, it's best to stick with normal mode. We will demonstrate Mavlink link mode in practice in a separate flight video. The last basic setting is TX power, which determines how much power the transmitter uses to send the radio signal. Values start at 25 mW and can go up the maximum supported by your module, in this case 1 watt. In LBT mode, power is limited to 100 mW, so in Europe that will be your maximum available setting. Here I previously installed ISM FCC firmware to show the full available range. Higher power means better range and signal penetration, but that doesn't mean you should always use the maximum. Tests show that even at 2.4 GHz and 100 mW, you can reach distances of 10 kilometers. Higher power also means increased battery consumption on your transmitter and more heat generated by the module, which triggers the cooling fan. The default fan threshold is 250 mW, meaning the fan turns on at that power level. There's also an option called dynamic power, which automatically adjusts the transmitter output power. When enabled, the system adjusts power based on link quality using the signal to noise ratio rather than just signal strength, making it more accurate. In practice, this means that when your model is close, the power stays low, and as it gets farther away or the signal weakens, the power increases. This is a very useful feature. It helps save battery when conditions are good and boost power automatically when needed to maintain a reliable link. Choosing the maximum transmit power mainly depends on how you plan to fly and the packet rate you selected earlier. With low packet rates like 50 Hz, you can achieve extremely long ranges even and relatively low power levels around 100 mW. On the other hand, with higher packet rates, the range will be shorter, so it's often compensated by increasing the transmit power. In practice, for most users flying within a few kilometers, 100 mW is more than enough, even at higher packet rates. That said, for those aiming to push distance records, reducing the packet rate is a key factor. As mentioned earlier, this significantly increases signal sensitivity, which often has a greater impact than simply increasing power. You will also notice options to assign different aux switches. This is a simple feature that lets you boost transmit power on demand using a switch. It can be useful if you want the full manual control and the ability to increase power in case of signal drops. At this point, we've covered essentially all the most important ExpressLRS features you need to fully understand to configure your aircraft to suit your needs. Don't forget to subscribe and follow the next videos in this series, where we'll dive deeper into other aspects of electronics. See you on the next video.